Hi, I'm Chase Marungu, and this is my final project for PHYS 282 Renewable Energy. So, for my final project, I wanted to make a sort of basic field lines or streamlines visualization for electrostatics and magnetostatics. The code is on GitHub, and it's also you can run it on in a web browser. It even works on a phone web browser on chasemarungu.github.io/sts282 final project. So you can see we have a starter scene here, and it's kind of complex, so I'll get to that. So the first thing you should know are there are two fields that this plotter currently supports. There will be more features I'll add in the future though. So with the electric fields, I'm currently supporting point charges, and line segment charges are currently a work in progress. So you can add point charges of positive and negative charge. This is what's known as an electric dipole. And the field lines will move away from the positive charge because a positive test charge would get repelled by it, and towards the negative test charge. Towards the negative point charge because a positive test charge would get attracted to that one. And you can test different configurations of electrostatics with the electric field. And if you switch to the magnetic field, I currently support infinite wires. So if you have an infinite wire and this is the plus z direction, then the field lines will move counterclockwise around the plus z direction. So that's the right hand rule, curl rule, right? I also support rings of current. So for this one, it's the current that's actually moving counterclockwise around the plus z direction. So in turn, the field lines want to move counterclockwise around the current at every point. So they're always moving counterclockwise around the current, which means they come in from through the ring this side and go out this side. And you can kind of combine, even with just rings, I want to add more in the future, more current distributions. But even with just rings, you can currently make things like this is a Helmholtz coil, consists of two rings of current, and it makes an okay approximation of a uniform magnetic field inside of the center given how simple the design is. And if you add more rings of current, you can build what is known as a solenoid. Let's see if we can get just a few in here. So if you add a lot of rings, the more windings the better, because of the superposition principle. Then you can create a solenoid. And the thing about solenoids, they're used all the time in engineering. They're a very fundamental thing in magnetostatics and just the physics of electromagnetism in general. This is an approximation. Usually, you'll have one wire of usually copper wire, and you'll loop it around itself multiple times. But for the mathematical approximation, we like to model it as if it is several different rings of current. And so each of these, the current is all flowing counterclockwise in all of them. And so as a consequence, these field lines want to loop counterclockwise around where the field line is moving through the screen. So if you look closely in the center, we actually do get a pretty decent approximation of a uniform magnetic field, which is what makes solenoids so useful. You can also combine where it gets really fun is you can add other objects like an infinite wire of current. Okay, I didn't do that right. Well, you can move the rings around and you can see the magnetic field will try to go through all of them. So the field lines will try to go counterclockwise through all the rings in the direction so that the plus C corresponds with the counterclockwise. And you can also add current infinite wires with current in them, which is it's a current distribution that doesn't have any. It's a divergence-free current distribution, even though you can't actually have an infinite wire in real life. You can have an approximation by having a very large loop, and you can combine them with rings and kind of see what happens. So now you get this sort of battle between the ring and the the wire where the field lines want to go counterclockwise around the wire, but they also want to go counterclockwise around the ring. So they kind of do this dance of going through the ring counterclockwise around the positive side of the ring, and then going counterclockwise around the wire, and then coming back up again, and then going through the ring again. And they make these very bizarre shapes, and that's what makes this project so fun to play around with. Is you can kind of combine, you know, all kinds of distributions and see how the field lines try to make sure they're always going counterclockwise around positive currents. So yeah, and that's now we get back to the starter scene, which had a sort of a solenoid and then also an infinite wire of current. So I thought that it was pretty fun to see these shapes and how they relate to the underlying physics of electromagnetism. Um, I hope you enjoy my project, and I will say I plan to add a lot more to this project in the future. This is just an early prototype that I could get done in one semester. Thank you for watching.